Hello, this is project number 2617, the optimization of hydrometallurgy in mining through automation. This project is sponsored by Freeport McMoran. Hydrometallurgy is the use of solutions to extract resources. For this project, our design will be using sulfuric acid to extract copper oxides and sulfides from ore. A raffinate container is filled with sulfuric acid that gets pumped into a tubular column filled with ore. As the acid makes its way through the ore, a pregnant leach solution is produced that is rich with copper molecules. Freeport was using a pump to dispense the acid, but these pumps would regularly become uncalibrated. And the calibration process for these pumps are very labor intensive, and there was no way to measure the moisture content and the temperature of the ore column, or the pH and the oxidation reduction potential of the pregnant leach solution during the process. Hi, I'm Everett Koga, a systems engineer and the team lead for this project.
Hi, I'm Jack Tews. I'm an industrial engineer and the procurement lead for this project.
What's up, guys? My name is Javier, and I'm the mechanical lead.
Hi, my name is Raji, and I'm the industrial lead.
Hi, I'm Jonah Ferguson. I'm the mining engineer.
Hi, I'm Daniel Gallardo, and I'm a software engineer.
Hi, I'm Arjun Moore, and I'm the electrical engineer for this project.
The objective of our project is to develop and prototype a piece of lab equipment that automates a hydrometallurgical system. This objective includes goals such as delivering raffinate via gravity-fed solution, has 3 flows, 38 milliliters a day, 95 milliliters a day, and we're 95 milliliters a day, measures moisture content and temperature of the column, measures pH and ORP of the PLS, verifies that the system works, alerts for leaks and failures, is scalable, and is low maintenance.
Our approach to the problem promoted simplicity over complexity. We identified the pumps as the point of failure in the existing system, as they needed calibration constantly. Therefore, we decided to replace them with a gravity-fed system that completely eliminated the need for calibration.
One of our central system requirements relates to the delivery of raffinate. Our system had to be configurable for 3 different daily doses, and it had to deliver each of these continuously and stably. The other key system requirements relate to the integration of sensors. Our system needs to monitor and record the humidity and temperature within the ore column, as well as the pH and oxidation reduction potential of the PLS as it exits the ore column. It also needed to check for sensor failures or invalid readings and set up indicators to alert the user to such failures. In addition to this, all our system components need to be compatible with the acidic raffinate solution they will contain. Furthermore, due to the extensive testing cycle, the system needs to require as little maintenance, calibration, and other user intervention as possible.
The design we developed to achieve our system requirements is a gravity-driven drip system. This was done to eliminate the need for pumps, thus reducing calibration issues. To ensure precise flow, we used a control head pressure and flow restrictors. The system included a raffinate container, which held the acid until it was ready to be released into the system, a flow control mechanism utilizing a pitch valve to start or stop flow, an ore column setup with multiple sensors to analyze the leaching process, a custom-made sensor block that allows for constant sensor submersion, and a PLS container that captures the resulting fluid.
We were able to verify our requirements and ensure that they passed the limits and constraints that were set. Briefly going over some of our requirements and how they were verified, the system is able to deliver doses of the raffinate solution at 3 different rates. This was tested by repeatedly measuring the amount dispensed and seeing if it fell within the expected 10% range consistently. The system is equipped with sensors to measure the pH levels, temperature, oxidation reduction potential, and humidity. We verified that they are calibrated and can collect readings as instructed by their supplier data sheets. And lastly, the system will alert the user on dosing and sensor reading errors. This was verified by performing tests with cases that will cause these errors.
The data we collected for our project illustrates our ability to achieve highly consistent dosing. Our lowest flow rate setting, which has the tightest tolerances of the 3, illustrates this perfectly. We took over 600 data points for this setting, all of which are plotted in this chart. The high stability of the output dosage is evident with each data point landing well within the 10% error margins provided by our sponsor. For all 3 flow settings, our system is able to dose within the error margins from the maximum fill of the reservoir down to the minimum fill and continues to do so upon refill. The sensors we selected require infrequent recalibration, and the data logging script we designed consistently records sensor data. This combination demonstrates that our system successfully and reliably automates the hydrometallurgical testing process, requiring minimal user intervention during the testing cycle.
We will be delivering a fully functional prototype to Freeport along with design documentation that includes our system requirements, schematics, and analyses. All test data and results will be delivered as well. An operation manual and maintenance guide will be delivered to support users that will be utilizing the system.
So first, I'm going to flip this little valve right here, and that's going to allow flow to come down from our top hopper and go right through this system. As you can now see, our flow meter will light up when we get our next dose, and that indicates that flow is actively occurring. And now flow is starting to come down here. Here we have our pinch valve, which is controlling our flow with a correction coefficient that accounts for time in accordance with flow that comes out of up here in our hopper. Here we have mounted a temperature probe that will come through this hole, and this is our humidity sensor that tells us a bunch of analytics about what's going on in this column and the ore processing that's happening within it. Here we have a live feed of the actual flow rate going through the machine up top here within our CDE1. Now for our critical design element 2, this is a sensory manifold for our pH and ORP sensors that will rest right in here. Now this area contains a body of fluid for its entire life cycle. This is key to keeping both of these sensor tips wet at all times to make sure dry out does not occur and that those sensors are not scrapped. It will always maintain a constant body of fluid. Air brake comes in here to allow air so a siphon effect does not occur, and it will leach down our finished PLS solution into a PLS container. Here I have an example of our electrical box that holds our pH and ORP boards as well as our isolation boards. And as you can see, we have pH in red here on my right and ORP on the left. These are the 2 areas in which you can connect your pH and ORP probes, which actually take in the data. And here is where it will send and receive power up through here with jumpers going to your Arduino. Now this will just clasp right on like that. As you can see, stays right on, super easy to put on, super easy to take off.
Our team learned a tremendous amount on this project. Starting off with our CDE1, our dosing system up here, we encountered a variety of issues encompassing electrical noise that our team handled hand and fist. Then coming into our CDE2 right down here, we experienced a massive material science challenge in which we had to understand how to get 5 separate types of material all to work together that were all acid proof that could form this entire block to keep a full body of fluid in here and both of our sensor tips wet at all times. This was both a physical and a material science challenge that really brought our team to the brink and kept us in it.
We wanted to say thank you to our sponsors, Jody Robertson, Sarah Leons, Ryan Campbell, and our mentor, Mike Majerick.